Okay, welcome back. Let's now look at Go backend on an example to see how it works. Here we assume that n is 4, so the window size is 4. And therefore the sender can send 4 packets before it has to wait for the ACK. And here assume that packet 2 is lost. So because Go backend uses cumulative ACK, so when the receiver receives packet 3 with a gap, it's going to send ACK of 1, okay, because it has received everything up to packet 1 without the gap. So it sends ACK of 1 again. Now let's look at the sender side. When the sender receives ACK of 0, it's going to slide the window. Now it can send packet 4. And when it receives ACK of 1, it can slide the window again. And it's going to send packet 5. Now, packet 4 and packet 5, they are received okay, but there is still the gap of packet 2. So receiver keeps sending ACK of 1, right? ACK of 1, ACK of 1. Okay, in the meantime, on the sender side, remember there is a timer with the oldest unacknowledged packet is packet 2. Okay, packet 2, so there's a timer running for packet 2. And packet 2, that timer will expire at this point in time. Okay, it will expire. Now, when the timer expires, the sender will retransmit all the packets in the window which are yet to be acknowledged. So it will retransmit 2, 3, 4, 5. 2, 3, 4, 5. So here you can see that it can be inefficient, right? Because 3, 4, 5 have been received, but they are discarded by the receiver. So the sender has to retransmit. Okay, now when it retransmits packet 2, let's assume that this packet 2 is now received okay. So packet 2 is in order. There's no gap. The receiver will deliver packet 2. Now it's going to ACK 2, send a ACK of 2, right? It has received everything up to packet 2 without a gap. And then packet 3, it will send ACK of 3. 4, it will send ACK of 4, and then 5, it will send ACK of 5. Okay, any question on Go backend? I think this slide is very useful to understand Go backend. All right, so let's look at selective repeat. Selective repeat, the ACK has a different meaning because it's an individual ACK. So every time the receiver receives correctly a packet, it will ACK that packet. Okay, so it will ACK the sequence number of that packet. And the implication of that is that the receiver must buffer the packet if the packet is received out of order, because that packet will not be retransmitted by the sender. And the sender only needs to resend the packets for which the ACK has not been received. And like the for RTT 3.0, we need to have a timer to deal with packet loss. So there will be a timer associated with each unacknowledged packet. Okay, so in the sender window, we will have n consecutive sequence numbers. This is that sliding window, and that will limit how many packets can be sent. Okay, so that's the concept of sender window. Okay, now in the case of selective repeat, let's look at the window at the sender and at the receiver. This is the window at the sender. This is the window at the receiver. So you can see right away, one difference with go back N is that I told you that the receiving window is by definition the range of sequence numbers which are accepted by the receiver. Now, in the case of go back N, the receiving window is only one sequence number, right, which is the expected sequence number. But in the case of selective repeat, the receiver window has the same size as the sending window. So if the sending window is N, the receiver window is also size N, because the receiver will accept out of order packets. So it needs to accept more than one packet, more than one, right? If it receives, for example, packet 1 and then packet 3, with packet 2 missing, it needs to accept packet 3. It needs to accept packet 3 and save it. So packet 3 needs to be in the receiver window. So we can see right away that the receiving window is wider than in the case of go back N. Okay, let's look at the sending window. So like before, we have send base and we have next sequence number, and they have the same meaning as in the go back N, right? This is the lowest sequence number in the window. This is the sequence number that can be used next for a new packet. And then N is the parameter, which is the window size. Okay, so now we can see that there's a difference with go back N, because in the case of go back N, we only had two types of numbers in the window. We only have yellow and blue, if you remember, right? Yellow meaning sent, not yet act, and blue means usable, not yet sent. But in the case of selective repeat, we have three colors. We have three. We can also have already act, the green ones. Okay, so here, for example, we have green ones, a few green ones, we have yellows, and we have blue. Essentially because the sender may receive. So let's say that, for example, this is packet number 5, right? This is 6, this is 7, this is 8. So the sender may have received 7, ACK of 7, but not receive ACK of 5. Okay, and because it's an individual ACK, ACK of 7 simply means that packet 7 has been received, but packet 5 has not been ACKed, because the ACK is not cumulative. So that's why we have three colors, because as long as packet 5 is not ACKed, the window cannot slide. It cannot slide the window. It has to stay here, wait for the ACK of 5. So the window stays in this send base equal 5, but the sender may receive ACK of 7. It may receive ACK of 8. So all of that needs to be recorded at the sender, because it has to remember that, so that it will not send packet 7 and 8 again, right? And that's why we have another third type, which are the already ACKed packet, shown in green at the sender. Any question here on the sending window for selective repeat? Okay, if not, then let's look at the receiving window. So here, the sequence numbers, the bars which are vertically aligned, they have correspond to the same sequence number. Okay, so let's assume for concreteness, this is 5, 6, 7, 8, 9. So this is number 9 at the receiver. Okay, so the receiver maintains this state variable, which is called receive base, and essentially it is the lowest sequence number of the receiving window. In this example, it is 9. It is 9. Okay, let's look at what we have inside the window. We have three types. We have three types of packets. We have the ones that has been received okay, but out of order, and that have been buffered. And that is shown in purple here. Okay. We have the ones which have not yet been received, and that is shown in gray. And then we have the ones which have not been received but acceptable. In other words, if the receiver receives a sequence number that are one of these blue, right? Which are one of these blue, then it will accept them. They will be accepted. Okay, acceptable. They fall within the window. 21450 Okay, sorry. Okay, so here the receiver will not slide the window until it receives this number, until it receives packet number 9. As long as it does not receive packet number 9, the window will stay here. Okay, now a quick question for you. Let's say that the receiver is in this state. So we have the receiver window which looks like this, and the receiver receives packet 9. What's going to happen to the receiving window? It's going to slide. Who thinks it's going to slide? No? Well, why doesn't it slide? Anybody else? Slide to 12, so 9, 10, 11, yes, correct. That is the correct answer. It's going to slide to 12 because if it receives ACK of 9, then 9 has been ACKed, right? 10 has been ACKed, 11 has been ACKed. So it can slide all the way to 12, and then it stops at 12. So the new receive base will be 12 because that's what is going to wait next, right, to receive. Okay, and this is selective repeat. Essentially, in selective repeat, the receiver will slide as far as it can to the right, and then it will stop at the one that is not yet ACKed. That's essentially the rule. Sorry, it will stop at the first one that is not yet received. At the sender will slide to the right as much as possible, and it will stop at the first one that has not yet been ACKed. Okay, now another question for you. So this could be a snapshot of the windows at the sender and the receiver taken at the same time, right? I take a snapshot, and I have the windows that look like this. So here I see that the window under is kind of behind, right? It starts at, was it 5, right? That was my example, 5 for the sender. But the receiver is ahead because its window starts at 9. So why is that the case? Why is it that we have this kind of misalignment between the two windows? Okay, because of the missing packets. So actually, hold on. I think that there's a chat that I haven't answered. So there's one which asked, you set at grade 1. Is that, you still have that question, or is that been answered? You said at grade 1. Okay. No, I think that was a question from Mohammed. You said grade 1. That is the question I'm reading. Is that you still have that question? Okay, you're good. Okay, yes, because of the missing packets, yes. And this is a very good example from James that the receiver did receive 5 and 6, right? Did receive 5, 6, 7, 8. It sent back ACK of 5, ACK of 6, ACK of 7, ACK of 8, but the ACK of 5 and 6 were lost. So the sender did not receive ACK of 5 and 6, and therefore 5 and 6 are still in the state not yet ACKed. Okay, 5 and the sender received ACK of 7 and 8, so they're marked as green. But as far as the receiver is concerned, it has received 5, 6, 7, 8. So it slided the window. It has slided its window to the right, and it stopped at 9. Okay, that's exactly the reason. Now, another possible explanation could be simply because of the delay, right? So perhaps ACK of 5 and 6 are not lost, but they are still in transit, but not yet received by the sender. Okay, so that's why there's a lag. There's a lag between the sender window and the receiver window. Okay, I think I addressed all the questions. Is that correct? If there's still some question that I have not yet addressed, just type your chat again. Go ahead, James. Does the sender resend 5 and 6? Yes. So the sender will resend 5 and 6. And then my next question for you, since you are asking the question, I can ask you also another question. I think that's fair. When will the sender retransmit 5 and 6? So 5 and 6, ACK of 5, ACK and 6 were lost, right? When will the sender retransmit 5 and 6? Eventually, yes, correct, after timeout. So remember, there's a timer associated with each of the number, right? There's a timer for 5. There's another timer for 6. So when the timer for 5 expires, the sender will retransmit 5. Okay, and then I think there's another comment. What happens since 5 and 6 are unusable at the receiver? Okay, so what happens is the receiver will receive 5 and 6, but it will simply send it back and then ignore them because it knows that those are duplicates. Those are essentially duplicates because the ACK was lost. Okay, 5 and 6 are unusable. They are unusable, but the receiver will not totally ignore them. It will still send back an ACK because to send back an ACK, otherwise the sender will not be able to slide its window, right? Otherwise it will be stuck here. So it needs to send back the ACK to allow the sender to slide the window. Okay, and then I think I have another question from Andrew. So if the receiver sends an ACK to the sender, the ACK will move the window. The ACK will move the window. So here, I guess that you are talking about the receiving window. Yes, you're talking about the receiving window. Yes. So yes, it will when it receives a packet correctly, it will slide the window if it can, right? Okay, I think I have addressed all the questions, but those are very good questions. Okay, so let's do the second checkpoint. Okay, another question. As the window keeps sliding, they will come back to 0 again. Yes, because we have a limited number of bits of the sequence number. So if it runs long enough, we will have to wrap around and go back to 0. Okay, so let's do the checkpoint. What is that? I think the next one is 6-1. Excuse me. Okay, so we have enough checkpoints for today, I think. All right, let's look at selective repeat. So this is a logic at the center. When it has data to send, it will check if there's an available sequence number in the window. If then it will send the packet. Now it will start the timer. Remember, there's a timer associated with each packet. So if that timer times out, right? If we have a timer for the timer associated with packet number n, then it will resend the packet n and it will restart the timer. Okay, when it receives an ACK of n, ACK of packet number n, and it will simply mark the packet n as received. So if the ACK is in the window, okay, it will mark the packet as received, and then it will attempt to slide the window if it can. So if that n is the smallest unacknowledged packet, it will advance the window as far to the right as possible, and it will stop at the first unacknowledged number that it finds. Okay, so it may move multiple notches to the right. Okay, at the receiver, receives a packet n that falls within the receiving window. This is a receiving window. Then it will send the ACK of n. If the packet is out of order, it will buffer the packet. If the packet is in order, it will deliver the packet. But it could be that it will, in this case, it may deliver multiple packets because, for example, if packet 2 was missing, right, but it received packet 3 and 4 previously, then when it receives packet 2, it will deliver packet 2 and packet 3 and packet 4. And it will advance the window to the next not yet received packet. So in this example, it will advance the window to packet 5. Now you may have this kind of situation where packet n is the receiver receives packet n, but packet n is outside of the receiving window. So this corresponds to the case of, remember, the packet 5 and 6, the ACK of 5 and ACK of 6 were lost, right? So the sender timeout and then resend packet 5 and packet 6. And packet 5 and packet 6, they are actually now outside of the receiving window. So the receiver should still send back ACK of 5 and ACK of 6. And then this case, otherwise, so this is a kind of none of these two cases. So ignore, so this is a kind of abnormal situation, okay? So normally the receiver should receive a packet in the window or a packet which is in this range on the left of the window. Any question? Okay, let's look at selective repeat in action. So we also have a window size 4. And like before, the sender sends 4 packets before to stop and wait. Oh, sorry. And we also assume that packet 2 is lost. Right, so now the acts are individual acts. So we go act 0, act of 1, act of 3, right? And this packet 2, when it was transmitted, had the timer started associated with packet 2. So when the timer expires, it will resend packet, but only packet 2. Okay, now let's look at the sender side. What happens when it receives ACK of 0, ACK of 1, ACK of 3? So ACK of 0, 0 is here the first one in the window, so it can slide the window. 1 is also now the base, so it can slide. But then it receives ACK of 3. It cannot slide the window because it has not received ACK of 2. Okay, so it just need to mark that ACK of 3 has been received. And it received after that ACK of 4, so it marked also ACK of 4 has been received. ACK of 5 has been received, but ACK of 2 has not yet been received. When this timer times out, it sends packet 2, and now I assume that packet 2 is received okay. So at the receiver, it received packet 2, it can deliver packet 2, but it also buffered 3, 4, and 5, so it can deliver 3, 4, and 5. And now it sends ACK of 2 because it received packet 2. Now question, what happens? What happens at the sender when ACK of 2 arrives at the sender? What's going to happen to the... Yeah, slide forward, but how much? Well, yes, it will move to 6 because it is packet 2 has been received, 3 has been recorded as received, as well as 4 and 5, so it can slide all the way to 6. Okay, so now let's look at this interesting. Let's assume that I use 2 bits for my sequence number. So I'm going to have 0, 1, 2, 3, and then I will wrap around to back to 0, right? I have only 2 bits. And let's assume that my window size is 3. Okay, let's look at this scenario. Window size is 3. The sender sends 3 packets. And this is the window at the receiver, right? It receives 0, so it slides. Receive 1, it slides. Receive 2, it slides. So the receiver will accept packet with sequence number 0 again, right? Because this is normally not a duplicate. This is another packet, but because of the wraparound, so it's a sequence number 0 again. Now the sender sends packet 3. The sender receives the ACK. It slides the window, sends packet 3. Packet 3 is lost. Okay, sorry. Packet 3 is lost. But it received this ACK, which is ACK of 1, right? So it slides the window again, and it can send packet 0. It can send packet 0. Okay, this packet 0 is a different packet. This is not a duplicate. This is a new packet 0, and it will be accepted in the window. So there's no problem here. Everything is fine. Okay, now let's look at the case B, another case. Okay, so here there's a curtain, simply meaning that the sender does not see the receiving window, right? and the receiver cannot see the sender window. Okay, it's like as if there's a curtain that separates them. Okay, now let's look at this case. So the sender also sent 3 packets, 0, 1, 2. They are received okay, right, at the receiver. So the receiver moves its receiving window, sends back the ACK, but now all the ACKs are lost. Okay, lost, lost, lost. The sender will time out, waiting for the ACK. So it times out and it will transmit packet 0. Packet 0, okay? Now what happens is, this is a duplicate, right? These 2 packet 0 are duplicates. But as far as the receiver is concerned, there's no difference between these 2 cases. The receiver receives packet 0, 1, 2, sends back ACK of 0, ACK of 1, ACK of 2, right? In both cases. Now, when it receives this packet 0, it will accept it as a new packet. It will not know that this is a duplicate because there was no difference between the 2 scenarios, right? It will accept packet with sequence number 0 as a new packet. So obviously there's something wrong here. We have an incorrect behavior of the protocol because we have duplication. Okay, so question for you. So if we try to think about why that happens, what are the reasons? Why is it that we have this problem? And then if we know why, then we can know how to solve the problem. But first, why do we have this problem? Why is it that in this case we cannot distinguish, or the receiver cannot distinguish between these 2, does not know that these 2 packets, packet 0, are duplicates? Turnaround is too short. What do you mean by turnaround? Can you be more precise? You mean time turnaround, or is it sequence number? What is it? Yeah, sequence number. So you mean it wraps around too early, right? Is that right? Yes. So here we could solve the problem if we didn't wrap around to 0. So for example, if we have 1 more bit for the sequence number, then this, instead of 0, we would have 4, right? 4, not 0, 4. And then there will be 5. So the receiver will not have 0. It will not accept this packet 0. Well, it knows that this is a duplicate at least, right? Okay, so one way to solve the problem is to extend the range of sequence number to be more than 4 values. What could be another way to solve the problem? Yes, make window size smaller, correct. So if we make the window size, for example, 2 instead of 3, yes, I will answer your question. Not sure exactly how small. So let's assume that we make the window size to be 2 instead of 3, right? Make it smaller. Keep the same sequence numbers. Okay, so here we will send only 0 and 1, but at the receiver, the receiving window will be 1 and 2 only, and then 2 and 3 only. And then it will time out, it will retransmit 0, but then 0 will not be in the window because the window is only 2 and 3. Okay, so that will also solve the problem. So here we see that So on this example, we see that, okay, we could solve the problem by having a larger range for the sequence number, or we could have a smaller window size. So in general, so the general solution to the problem is that there is a specific relationship between the sequence number size and the window size. And the relationship should be that the window size can be at most half of the range of values. So here I have 4 values. My window size can be at most 4 divided by 2, which is 2. Okay. And if you are interested, actually, I think there's a problem in the textbook where they ask you to prove that statement. But that statement is true. So when you design a selective repeat protocol, you need to make sure that when you choose the window size and you choose a number of bits for the sequence number, they should be such that this problem doesn't happen. And that means you need to have enough bits for the sequence number for a given window size. Okay, so either you have to make window size small enough, or you need to have enough bits for your sequence numbers. Okay, so relationship is window size is 1/2 of the range of sequence numbers. So James, that answer your question? Okay, so that is the end of this unit. Let's go to the next one, which is unit 10. Okay, so we have learned about reliable data transfer in the stop and wait. And then we saw that stop and wait is kind of low performance, right? Because we have to wait for the act. So the way to increase the performance is to use a pipeline or sliding window protocol. And then we learned about, okay, the different ways conceptually how you can do reliable data transfer when you have pipeline protocols. And essentially, there are these 2 conceptual protocols, which are selective repeat and go back N. As I said earlier, selective repeat and go back N, they are not actual protocols used on the internet. So now we're going to look at the actual protocol used on the internet, which borrows many of the concepts that we have learned in selective repeat and go back N. And that protocol is TCP, or Transmission Control Protocol. By the way, if you look at the traffic on the internet, in terms of volume, more than 90% uses TCP. Okay, more than 90%. So you think about all these things like YouTube, streaming, Netflix, and so on. They all use TCP. When you do web browsing, it also uses TCP. So there's a lot of volume of data, right? Okay, TCP is a protocol that is defined in many documents. These are some of them. These RFC documents. Okay, when you use TCP, you can communicate point to point, meaning that there's 2 endpoints to your TCP connection, A and B, right? And TCP provides a service to the application layer. TCP is a protocol in the transport layer. It provides the reliable in-order byte-stream service. And because it's byte-stream, there are no message boundaries. So what the receiver receives is just 1 byte after another but there's no delineation, right? There's no delineation telling the receiver this is the beginning of the second message and this is the end of the second message. It's just byte after byte. But the stream does not necessarily have to arrive continuously, right? You may have idle times. TCP is a pipeline protocol. It uses a sliding window. Now, we will see later when we learn about TCP congestion control and flow control that TCP is pretty sophisticated because it will dynamically adjust the window size. Okay, remember that parameter, capital N, uppercase N. We just assume that it is a parameter, which is the window size. But in the case of TCP, the value of N is dynamically adjusted. TCP is bidirectional. So when you have a TCP connection between A and B, A can send data to B and B can send data to A. And one parameter of TCP connection is called the MSS, which stands for maximum segment size. Essentially, it is, you can think of it like the maximum packet size. TCP has flow control so that the sender does not overwhelm the receiver. TCP is connection oriented, meaning that before you can actually transfer data, you need to go through a phase where you set up the connection, the TCP connection, and you do that with handshaking. Okay, you need to exchange some control messages to set up the TCP connection. Okay, this is the TCP header. So just to take an example, remember HTTP protocol, right? You have HTTP request message and you have the HTTP response message, and HTTP runs over TCP. So the HTTP request message is handed over to the TCP socket, and the TCP socket, TCP will receive that HTTP request message, will add this TCP header to the HTTP request message. Okay, and the whole thing is called a segment, a TCP segment. This whole thing is a TCP segment. Okay, let's go through some of the important fields in the segment. So the source port number, destination port number, they are the same as in UDP, and they have the same meaning, right? They are used for multiplexing, demultiplexing. Okay, next we have the sequence number. So remember the in the pipeline protocol, go back N or selective repeat, we have sequence number attached to each packet, right? And more or less, the assumption was that, okay, you send the sequence number is the 1 for the first packet, and then it increments at each packet, right? So 1, 2, 3, 4, and so on. Now, in the case of TCP, the sequence number is does not count the number of packet, does not count the packet, but it counts the bytes. Okay, so we'll get back to that later. But conceptually, it is a sequence number. Okay, we also have an acknowledgement number, and that is used for the ACKs, right? When you send back the ACK, you need to ACK what? ACK packet number X, right? So that will be the X here. Okay, and then we have the header length, and this is needed because the header, the TCP header, can have variable length since there are some options. So depending on how many options you have, okay, your length can vary. Okay, so you need to provide the length information, and then there are some 1-bit flags, which are the one here. Later we will see how they are used. Okay, there are some of them which are very important that are used here. We have the receive window field, and this is sent by the receiver to the sender to tell the sender how many bytes are available in the receiver buffer. So this is used for flow control, right? So for example, if the receiver has 1,000 bytes left in this buffer, it will send back 1,000 here. And the sender is not allowed to send more than 1,000 bytes until it receives further notice from the receiver. We have a checksum, which is like the UDP checksum, right? So it's used for error detection. Let's not worry about this one. It's not so much used, okay? All right, so these are the kind of the most important fields in the TCP header. So you can see right away that if you compare with a UDP header, a TCP header is bigger, right? It is also more complex to process. Okay, now let's look at the TCP sequence number. This sequence number. So remember, TCP provides a byte stream service, right? Byte stream service. So we have the application process that is sending to a TCP socket. And what it is sending is bytes, byte 51, 52, 53, 54, and so on. Now, what TCP does with these bytes is that it's going to build the TCP segments, and it's going to segment these stream of bytes. So here, I just assume that it's puts these bytes, so byte 51 all the way to byte 155 into one segment. Okay. So here, because the first byte of the data is byte 51, it's going to use a sequence number in the header 51. Okay, the next segment that will be sent will be byte 156, right? To, let's say, byte 200. So the sequence number of the next TCP segment will be 156. It is always going to be the byte, the number of the byte, the first byte in the payload. Any question on the TCP sequence number? So here in this example, the sequence number is 51, and then the sequence number of the next packet is 156. Okay, essentially it counts the bytes, not the packet. Are we clear on the sequence number? Increment by 1? No, it does not increment by 1. It goes from 51 to 156. Essentially, it models the data as bytes. Each byte has a number, right? And the number carried by the TCP header, the sequence number, is the number of the first byte in the payload, not increment by 1. Okay, now let's look at the TCP acks. So the acknowledgement has the same meaning, right? There's fundamentally the same meaning. It will be a cumulative ACK, like in go back N. But the difference is that if the receiver has received up to byte 320 included, the receiver will not send ACK 320. It will send 321. Okay, so that is a difference. Okay, so it will send the sequence number for next byte expected from the other side, +1. And also the other difference, of course, is that this number is the byte number, right? It's the byte count number. It's not the packet count number. And this acknowledgement number is carried in this field of the TCP header. And when there's an acknowledgement number, this bit, so there's a bit which is called act valid. This is a single bit flag, which will be set to indicate that there's an acknowledgement number. Okay, so when the receiver needs to act data, it's going to send a TCP segment with a header, and in that header, you will have an acknowledgement number. Okay, another question. How does the TCP receiver handle out of order segments? So this may happen, right? That there may be the receiver may receive segments with a gap. So what does the receiver do? Does it behave like go back end, meaning it will discard, or will it behave like selective repeat, meaning that it will save the segment? The answer is that the TCP specification does not say, they don't say, and it is up to the implementation. So you can implement a TCP protocol where you discard out of order segments, or you can implement a TCP implementation protocol where you save the out of order. And both will be compliant with the TCP protocol. Okay, let's look at another example here. So let's say we are running a telnet application. Essentially, telnet is a very simple application that mimics the terminal. And you can type something at the keyboard here. It gets sent to the other host, right? Okay, here I assume that the TCP connection has been set up already. And the user types the character C at the keyboard. So the character C is the data to be sent over the TCP connection. So that data will have a TCP header attached to it. And here I just assume that the sequence number is 42. And previously, here there's an implicit assumption that host A has received from host B up to byte number 78, right? Byte 78 has been received. So here host A will do two things at the same time. It will use this sequence number as a sequence number for the data that it's sending to B. It will use the acknowledge number to acknowledge the data that it has received from B using the same header. Okay, so what it sends here is the sequence number 42, acknowledgement number 79, and the data is the character C. Okay, now B is supposed to echo back the character C. So it will send data C as the data. Now, because it has received byte 42 in this packet, it's going to act 43, right? Acknowledgement number is 43. And the sequence number is now the sequence number for this byte that is sent by B, and it's 79 because it has received up to 78. Host A has received up to 78. It sends act 79, meaning that it expects to receive the next byte number 79. So this is 79. And then A will now acknowledge receives of this packet. So it will send act 80, right? It has received 79, up to 79. It's an act of 80. And the next sequence number, it has sent the byte 42. So now the next byte is byte 43. So sequence number 43, act 80. Okay, any question on this one? Okay, what is not clear? When you say not clear, you have to be clear about what is not clear. What part is not clear? 79 becoming sequence number. Sequence number, yes, because as I said earlier, host B, okay, ACK becoming sequence number. Okay, because, okay, let's look at this packet. Let's decompose it. Okay. Let's only look at the sequence number. Let's not look at the ACK. This packet has sequence number 42, right? Sequence number 42. B has received the ACK packet. So normally it should acknowledge that packet and it sends back the acknowledgement in the acknowledgement number. Now, because in TCP, the acknowledgement is not the number that has been received, but that number plus 1. So it sends back ACK of 43, ACK 43, right? Meaning it tells A that it has received up to 42. It expects to receive next 43. So is that part clear? Just look at the sequence number here and the ACK here. Do not look at this ACK and this sequence number. So what I just told you, is that clear? Okay, now, so that takes care of the data from A to B, right? Data from A to B has sequence number 42. B sends back an ACK 43. Okay, so data ACK. Okay, now at the same time, because TCP is bidirectional, so keep in mind that B is also sending data to A. Okay, A is sending data to B, B is also sending data to A. So let's look at this other part, the second part. B is sending data to A. So B is sending data, sequence number is 79. Okay, 79. This is sequence number of the data sent by B to A. Now A has to acknowledge, so it's going to send back ACK 80 because it has received 79. So it expects to receive 80 next. So that's what it sent here. Okay, so sequence number 79, ACK number 80. Okay, this is just the other direction. So does that help? So there are two directions that are operating at the same time, right? You have the sequence number. When A sends something to B, it attaches a sequence number of the data, but it is also attached an ACK number to ACK the data that is came from the other direction. Okay, it's bidirectional. So I think it's easier if you just decompose, right? Decompose it into two directions. Okay, now TCP also maintains a timer, because remember, we need a timer to deal with packet loss. Otherwise, the sender will wait forever, right, if the ACK is lost. So the question is, how does TCP set the timer value? Because it's not easy, right? It's not an easy question because, well, ideally, if we know the round trip time, there's no point to set the timer less than the round trip time, right? Otherwise, we're going to time out prematurely, right? So the timer should be at least as long as the round trip time. But the issue here is that the round trip time varies. Remember the trace route? When we run the trace route, we saw a lot of fluctuations in the round trip time, right? Even though we go to the same router, but the round trip time can fluctuate a lot. So we cannot set really a kind of fixed static value for the timer, right? But we don't want to set a value that is too short, because that will prematurely time out, and then we will unnecessarily retransmit. And we don't want to set the timer too long either, because that will slow down the recovery, to packet loss, right? Okay, so there's a suggestion from James, maybe increase the timer each time we time out. So actually, that's a very good idea, and that is used in some cases in TCP. But let's just wait a few slides. It will tell you how TCP basically calculates the timer value, and then there are some circumstances where they will increase the timer when they time out. Okay, so we don't want to set it too short. We don't want to set it too long. Okay, too long, it will slow down the reaction to segment loss, because if there's a packet loss, we don't want to wait excessively long before we will transmit. So the idea here is that let's try to estimate the round trip time, because if we have an idea about the round trip time, then we can set the timer value accordingly. And now we need to estimate the round trip time on a continual basis, because the round trip time varies. So first thing we're going to do is we're going to just measure the round trip time, meaning the time it takes to get the ACK, right? Because we have the ACK, send the packet, get the ACK. How long does it take? That will be the sample RTT. So it's a sample round trip time. Now, this sample RTT will vary. That we know, right? It may vary a lot even. So we are going to average it a little bit to make it smoother. Otherwise, it's going to be too much variation, okay? And this is the formula we're going to use to do the averaging. So this is a recursive formula that will give us the estimated round trip time. The estimated round trip time is the result after we do the averaging. So whenever we have a new measure, a new sample RTT, we're going to update our estimated round trip time using this formula. And if you analyze what we do here, this is recursive. This is a recursive formula. And it is exponential weighted moving average, meaning that the weight of the older sample RTT will decrease exponentially. Okay, it will decrease exponentially. A typical value for alpha. So alpha is a kind of parameter in the formula, but the typical value is alpha equals 0.125. Okay, I see that we need to stop now. So let's stop now, and we'll continue on Thursday. And thank you for your participation.